Good morning. Let me take some minutes to point out about the proceedings. There will be a special issue of Nuclear Physics B proceeding supplements devoted to the 10th edition of Silafae. And just let me to remember that we will have 100 papers to be published in open access, online and on press. And there are 10 pages maximum for the plenary speakers, 8 pages maximum for parallel talks, and in any case talks of maximum 20 minutes, and not more than 3 pages for the poster contributions. Strict deadline. February 15. 2015. Yeah. Yeah, everything is available on the website of our page of Silafae. Everything is there. So let's start by the first talk. First talker is Professor Gaston Gutierrez from Fermilab, Dark Energy Results.
That's okay, thank you. So anyway, good morning. Let me start by, like all the previous speakers, thanking the organizers for inviting me, but I actually want to do a little more. 2 days ago, I was sharing a taxi ride with another of the plenary speakers coming here, and we were talking about how well we have been treated. That, we have been treated, they make us feel really special. Even though we both knew that there is nothing special about us, we'd like to thank you for treating us so well. So, until a few years ago, I was doing experiments at the Tevatron, high-energy physics experiments at the Tevatron. And then Fermilab got involved in building the DES camera, and I thought it was a fantastic opportunity to go back and do some hardware, and also to get involved in a field as interesting as dark energy. So the DES is now running in Chile. In August of just a few months ago, started the second observing season. And of course, things, even though the data quality is extraordinary, things take time, so there aren't any final results about cosmology, parameters, and things like that from DES. Also, the telescope in Chile has a sister telescope in the north. Essentially, it's a copy of the telescope in the south. And now there is a project called DESI trying to build a spectrograph in that telescope, and given our experience, we are also involved building a spectrograph there. And of course, that experiment will not run until 2019, so there are no results for that. So instead of telling what happened with DES and what we are going to do with DESI, what I'm going to tell you is about the techniques that are used, not just by DES and DESI, the techniques that are used by everybody to measure dark energy and give you a sense of where the field is at right now. So I will talk a little about the props of dark energy. Then there are essentially 2 ways of measuring dark energy. One is measuring distances, and that actually determines the value of W very well. And the other one is trying to see if general relativity is correct. I mean, we are all assuming that general relativity is correct when we say that we need a cosmological constant or a parameter to describe that energy, but, general relativity could not be correct. So one way to actually test that is to study the growth of large-scale structure, and I will talk a little bit about that. And then I will go quickly over the future experiments. Of course, there is no way to cover what everybody else is doing. I will cover essentially the ones where the United States is involved, and also have my bias being a member of both DESI and DES. And so that will show my bias and my ignorance at the same time. And then I will conclude. So let me start with a little bit saying why it's dark energy. You all know that dark energy is what is producing the expansion of the universe. But it's stuff that is different because it has negative pressure. So matter, all known matter has positive pressure. Essentially means if you put a box with matter of any kind and you open the box, matter expands. It doesn't stay. You have to put positive pressure if you want things to stay inside the box. Now, the strange thing of general relativity is that actually that produces gravitational contraction. If you actually want to produce acceleration, you need something that actually that wants to contract. It doesn't want to expand, but wants to contract. But in other words, if you expand the volume, you get more energy than what you had before. So that you say that, that's very strange. It is, but that's the way black holes work. You say, well, why is it that black holes collapse? How do we know? After all, we don't know every force in the universe. But what happens is as you increase the pressure, as you increase the mass, you increase the pressure makes gravity to actually get stronger because you have more mass. If you have pressure, you have more energy, you have more mass. And then what happens is that there is a runaway process. So essentially, it's that positive pressure inside of the black hole or the star that is collapsing that wants to prevent gravity from collapsing that actually makes gravity to collapse the object. So you need something with negative pressure to actually produce acceleration. And one way to produce negative pressure is you have a volume, you expand the volume, you have more energy than before, like in the vacuum, and then that produces acceleration. You need a minimum, if you calculate the ratio of pressure to density, energy density, the equation of state, you actually need this number to be at least -1/3. It turns out that experimentally this number is extremely close to -1, but it has to be at least -1/3. So a gravitational constant is essentially something that you add to Einstein's equations. This is the energy momentum tensor. For an isotropic fluid, it's as this is just the energy density and the pressure. They have different sign. If you put here a constant, they all have the same number, so that means that the pressure is negative. Because if all these numbers are positive and this is positive, that means that the pressure of that object is negative. And it's not only negative, these numbers are the same, and then this number is -1. So if you have a gravitational constant, you have something that has negative pressure. Like I was saying, all the evidence so far is that that number is just that, -1. But, one is trying, if you're trying to characterize dark energy, what you really want to know if it is really -1 or if there is a deviation. So you can expand it. You can say there is a constant that is very close to -1, and then there is another thing that depends on time with another constant. So if you want to think about this, it's like the first term of a Taylor expansion. Sometimes it's parameterized in a way in which this is not 1, but this is some other number. And so the name of the game is trying to see if this is -1, and that number is different than 0. And then these are just the different probes, and I'm just going to cover some of them. So let me first say a little bit about where, if you want to study dark energy, where you go look for that. So at a redshift of about 6,000, 7,000, the universe started to be dominated by matter. So from there on, the fluctuations in matter are very small. You can linearize general relativity. When you do that, you're essentially using Newton's equations. So essentially, from here to here, you can pretty much describe the large scale of things essentially with Newton equations. At about a redshift of 1,000, so then things decouple, then the photons just went on their own, the protons actually went obeying Newton's equation again, and then about 1 billion years later, matter starts to form. And then it's only about halfway through the expansion of the universe that dark matter starts to show up. Dark energy starts to show up. So if you really want to understand dark energy, you have to come and study the universe in this regime. Of course, you can actually study the CMB very well, and then assume a model like lambda CDM or a model of your cosmology, and then you can, with that model, go and predict what happens here and check that the two observations match. And so far, they match extremely well. But essentially, if you want to make direct measurements of that energy, you have to come here and study this regime. In terms of redshift, you see that you are covering a redshift from about 0 until about a few, 2, 3, a redshift of 2 or 3. So that's in the visible. If you want to go cover this, then you have to go to higher redshift, and that's gets into the realm of radio waves, and I'm not going to cover that. So essentially, this shows a little bit the precision that has been achieved today. This is a scale factor. These are just co-moving coordinates. This is a scale factor of what is expanding the universe. And this is just a plot of the scale factor as a function of time. And you can see all these measurements, all these points in blue are supernova measurements. These are varying acoustic oscillations. I will tell you about that. And this is kind of what new experiments like this are trying to do. And those little deviations, this is a difference of W between minus 1.03 and minus 0.97. And this is what you're trying to do. This is what you're trying to measure. And this scale is very difficult to see. So already it's impressive what cosmology has done. I mean, the fact that this has been mapped at the level of better than 1% is just impressive already. So let me tell you a little bit about supernovae. You all know what supernovae are. There is one type of supernovae that behave in a really convenient way. It turns out that the way the intensity goes down as a function of time after they explode, it's related to the intrinsic intensity. So, you know, you can measure supernovas with the amount of light here and the decay time here, and you see that they are all different. If you actually expand this scale in time and correct for the intensity at the same time, you will find out that they all fall very nicely into one curve. So you can actually, by measuring the way this intensity decays, you can actually determine the intrinsic luminosity. And then if you know the intrinsic luminosity, you can infer from that how far this object is. So here is an example of the two more distant supernovae that have been identified. Of course, this has been done out from space. You cannot get to this level, to the redshift from the ground. And then you can see there is actually supernova right in that field. And then there is a difference. This is before and after, and that's a supernova. And then you can't see it here in this picture, but there is supposed to be a supernova right there, and that's at the redshift of 1.7. So this has been well studied. It has been published. And then, okay, before I show the publication, this supernova essentially exploded about 1.5 billion years after galaxies and stars started to form. So really, right now, with those supernovas, you can look back in time as far as that. So this supernova, if you actually, this is a measure of distance that I will define in a second, and this is a redshift. If you do that, that supernova is right here. Now, this curve has been measured with such precision that really most of the information comes from supernovas right here. And it's not only that. The statistics right now is high enough that the measurements are completely dominated by systematic errors. So if you just keep adding supernovas and you don't fix the systematic errors, then you don't gain much already. So that's why the ES is going to continue to look for supernovas and LSST2, and the idea is just to get a really control on the photometry. You are measuring the intensity that you get, and you really have to have an extremely good control of that in order to avoid systematic errors. So there has been a recent reanalysis of a combination of supernovas. Two experiments got together, tried to reduce their systematic errors, and those are the results that I'm going to present. But before that, the calculation of that curve is extremely simple. Anybody can do it. Essentially, this is a co-moving distance. That term is not very important. You can ignore it. This one is not very important. So there are really two terms. And if you only have a gravitational constant, this term here is just one. So essentially, you have two parameters. If W is not a constant, then you can just expand it a little bit. It's very simple. This, you put it in the computer. It takes no time to solve this. And then you just calculate what is called the distance motion, just by calculating the log 10 and doing this calculation. And that's what you compare your supernovas with. So this is just an example of just moving some of these parameters. In this case, when I moved omega matter. In this case, I just move omega 0. In this case, I move omega 0 and omega 1. with the same opposite signs. Here is the same sign. And this is the difference. You cannot see the difference in this scale. So that's how precise these measurements are. Now, you can also see that also this arrow indicates the direction of this number going up. So essentially, you see that if this number goes up and this number goes down, essentially they compensate. You essentially see no difference. So that's one of the problems of measuring W0 and WA, that essentially they fight each other. You can't, if you increase one and you decrease the other one, you really can't tell the difference. So that's what happens. This is just the combined analysis that was published in June of 2014. This is the same thing, just in a log scale that I was showing before. This is just that distance measure as a function of the log of redshift. But here is what I was telling you. If you change omega matter, let's say you decrease omega matter and then you increase W, then you can't tell the difference. So it's completely degenerate. And that's one of the problems. So you need a different probe in actually to eliminate that degeneracy. And in this case, it's Planck. Planck goes like this. So you have an intersection here that is very convenient. You can combine both results. And this is essentially the combination. This is the combination of everything. This is, in all the plots I'm going to show you, there are two contours. One is 68%, the other one is 95%. And then you can see this is a 68% contour. You can project it in here and determine the value of W. Of course, you can also choose any other two parameters and play the same game. It's very difficult to choose more than two parameters because of the correlations. So, you can choose another two parameters. You can choose WA and W0, play the same game. This is, again, it's 95%, 68%, 95%. Here, you assume that space is not flat, so you let WK vary a little bit, and then you can establish the relationship between these two. But the important thing is that W in these measurements is essentially to about 5% is -1. So this is the measurement combining the supernovas with Planck, assuming lambda CDM, and then it gives you a value of -1.018 plus or minus 0.057. And then this is a different combination which you combine with baryon-acoustic oscillations, and then you again see this value of -1. These are the best measurements so far of W. So if you're interested in W, this is the end of the talk. I mean, W essentially now is known to about 5.5%, that is -1. But the problem is, how do you go forward? Because once you get, as an experimentalist, once you systematic error starts to get you, it's very unpleasant because systematic errors are really difficult to deal with, are really difficult to calculate. You would rather have a technique in which you just add more data and the result improves. And this is not the case with supernova. It's difficult. So there are other techniques. The other technique is baryon-acoustic oscillation. And that technique is going to be dominated by statistical errors for a while. So let me tell you about that, doing baryon-acoustic oscillation using galaxies. This is a little bit about the evolution of the Fourier transform of these density fluctuations as a function of time, or C. If you are at C of about 3,000, then dark matter is completely decoupled from everything else. It's evolving by itself. It's just gravity. You cannot get waves unless you can push and pull. If you can only pull, there is no way to generate waves. So gravity, there is a structure. The structure doesn't change. All that gravity does is just increases that structure. The shape doesn't change. So that's what dark matter is doing. Just the shape is kind of more or less the same. It changes a little in this case, and I'll tell you why. But if you see the vertical scale, it's just the size. It's not absolute size. It's just, but the relative amplitudes are correct. So then you see here is 40. Then you go to another redshift of 1,000 is 80. You go to another redshift is 160. Another redshift is 1,200. In the meantime, before recombination, the protons, the electrons, and the photons are all coupled together. The photons with electrons through quantum scattering, the electrons with the protons because they are charged. And then in that case, there is a push and pull. And then you can generate oscillations. So you just generate these oscillations in that plasma. And at some point, that oscillations keep changing shape. And at some point, once you completely combine the electrons with the protons, there is no more pushing. And then these oscillations are frozen. And then they just evolve, but the pattern is the same. And those oscillations are known, that the distance of those oscillations is very well known. It's 150 megaparsecs. So that 150 megaparsecs stays in co-moving coordinates. It stays 150 megaparsecs even up to, until today. So you can actually go and measure that, and it's a ruler. You know the length of that ruler. So you make that measurement. This is another way of seeing the same thing but in space instead of in the Fourier transform. I'm not going to go over this. Axel actually showed it in one, Axel de la Macorra showed this in one of the parallel talks. He actually showed the picture and everything, so he did a really good job. I'm not going to do it again. So this is an artist's impression. You actually don't see rings. Of course, this is an artist's rendition. You don't look at the sky and see these rings. It will be too easy. So you have to do it in a statistical way. So you can actually pick a point, calculate the distance to all the galaxies, and then just get all the galaxies at a given distance, put them in a histogram, and then you get another distance. You do the same thing, and then you should see a correlation. Now, this is kind of a sphere. There are two measurements. Remember that as an experimentalist, you don't measure distance. As an experimentalist, you measure redshift, and you measure angles. If you want to know what this distance is far away, you have to assume a cosmological model to transform your redshift and your angles into a distance far away. And there are two distances. One is a transverse distance, that is essentially the angle that you measure times that distance to the object that you can calculate as an integral of the Hubble rate. And then it's a distance that is longitudinal. If this is the distance to the object, and then this is small, essentially this is a difference, and this depends on the Hubble rate, on the inverse of the Hubble rate. So it actually allows you to measure two things, the instantaneous Hubble rate and the integral of the Hubble rate between now and that object. But anyway, going back to the oscillations, you calculate this two-point correlation function, and this is what you see. This is the latest result from Bose. The data was released in June of 2014. Here is the peak. The peak is very clear. Now, it's not at the 150 megaparsecs because it's divided by age. The number that if you multiply by 100, you get the Hubble constant, which is about 0.7. But if you divide by 0.7, this gives you 150 megaparsecs. Now remember, in order to make this plot, you have to transform your measurements, your redshift, and your angles into distances. In order to do that, you have to assume a cosmology. In that cosmology, you get some parameters. So then you can adjust your parameters in order to get the result here that is 150 megaparsecs, or to get the oscillation here that you actually know. So that's the way you make the measurement. You adjust your parameters and you make a fit. And these curves adjust the fits, adjusting those parameters. And that's the way you determine these cosmological parameters. So you can do this. I mean, remember that I was telling you that you can do this in 3 dimensions. It turns out that at the beginning, people didn't have enough statistics, so they averaged. They made a spherical average, and the results were all doing in 1 dimension. You spherical average this, and then this essentially, people continue to do that. So this is essentially an analysis done on an average. And then the significance is extraordinary. You just calculate the chi-square between your prediction and your measurements, and now the chi-squares, they're absolutely parabolic. So this thing has been established to better than 7 or 8 sigma. Now, remember that I was telling you there is a transverse distance. There are actually 2 transverse distances. So if you want to transform, and 1 longitudinal one, if you want to transform this into 1 number, this is what is used. You put the transverse distance square just because it is x and y. The longitudinal distance, you get it to the 1/3, you get the distance, and then you compare that with predictions. And these are the 2 measurements I was just showing you, and this is the predictions of Planck. If you get the data from Planck, you assume lambda CDM, then you can make a prediction, you compare. So it's essentially you compare something happening at a redshift of 1,000 to something happens at a redshift of 0.5, 0.3, 0.4, 0.5. And the comparison is amazing, at least to me. So it's difficult to see here, just divide this by Planck. By definition, Planck is 1. If you use WMAP, it's a little, there's a little bit of a discrepancy, and these results just fall right in the middle. So there's perfect agreement, again, with lambda CDM. You can actually do the analysis. Now there is enough statistics to do the analysis in 2 dimensions, so you can do that. You can go to 2 dimensions. These are just, again, the peaks in 2 dimensions. These are 2 wedges. One is a longitudinal wedge, in the direction of observation. The other one is perpendicular. And you can actually do the fits now in 2 wedges if you want. And this is what you get. And from here, you can, again, extract your cosmological parameters. After all, you're assuming a cosmology. You are moving those parameters in order to fit. So at the end, you end up with 1 parameter if you assume a model, or 2 parameters if you just let 2 parameters vary. So these are just some of these contours. This is W and omega K. This is the combination with Planck and BAO. This is WA and W. But if you are just interested in one parameter, the value, okay, if you measure omega matter, you actually measure omega matter times the Hubble rate squared. So this is a measurement of omega matter from BAO, this is a measurement from Planck, and then they agree completely, even though they are just completely different redshifts. So now if you just combine everything, again you get -1, now with an error of 7%. So this is getting to the 5.5% of the supernovae. The big difference is that there is no systematic errors here. These measurements are completely dominated by statistical errors. This was done with about 1 million galaxies. DES is going to have 20 million galaxies, and the error is just going to go like the number of galaxies. So the nice thing about this is that very soon we will start dominating the errors, the measurement errors in W. So now, if you want to go very deep in redshift, then there is a problem, because these measurements are done looking at galaxies. The problem of looking at galaxies, DESI will stay about 20 minutes in each galaxy. Even though you can measure 5,000 galaxies at a time, once you have to stay for 20 minutes at a given galaxy, you can't stay 3 days at a given galaxy. So the further away the galaxy is, the bigger problems you have. So if you want to go to higher redshift, you have to move to a different technique. It's BAO, but you still measure this ruler, this 150 megaparsec ruler that is everywhere, but you have to do it differently. And it's very interesting. This is called the Lyman alpha 4. It's very interesting because about 2 years ago, I was in a room where people were talking about building a spectrograph to run after DES. And one of the problems to do this is you have to go into the deep blue. And you start running into problems with CCDs and everything, and people in the audience say, well, Lyman alpha 4s will never work. So we don't have to worry about that. We don't have to worry to go into the deep blue. That costs many millions of dollars more. Forget about it. It turns out that soon after that, they started, Boss started publishing this, and it's just astonishing. So essentially, the idea is you get a very distant quasar, which is essentially white. The light of the quasar reaches you. In the middle, it runs into hydrogen clouds. Every time it runs into hydrogen cloud, there are absorption lines, And then if you absorb very near, so this is the hydrogen in the quasar, which is the Lyman alpha line. And then if you absorb very soon after that, you get redshifted like the quasar. If you absorb very late, very close to you, it's in the blue. So essentially, you have a line in which you have mapped the amount of hydrogen in that line up to really high redshift. So essentially what you do here, you look between these two lines because it gets too complicated in here. So essentially you have the Lyman alpha line, you have the Lyman beta line, you look in between. So these are two examples of quasars. This is a near quasar. This is the Lyman alpha line from the quasar, the beta line. There is almost no absorption. Now this quasar has a redshift of 0.158. You go to something that's very distant, now things change completely. You have this absorption. This is all the hydrogen that there is between that quasar and us. So with all this absorption, you can actually determine the amount of hydrogen in that line. Now, if you have enough quasars, if you have plenty of them, then you're mapping the amount of hydrogen in 3 dimensions. And each one of these lines is like a galaxy, except that now, if you multiply the number of quasars, which in this case it was like 150,000 quasars, and you actually get all the pixels in that line, it's equivalent like 10 million galaxies. So you play the same game, you calculate the 2-point correlation function. Here is the way it is defined, if you want to see the details, and you get, voila, peaks. And the peaks are very well determined. Again, they has to be at about 100 megaparsecs over age, because we know that that's where they have to be, and you adjust your cosmological parameters to get that. So again, you can extract cosmology from this. And if you do that, again, these are the contours. I'm not going to get into the details of these contours. This is just the transfer distance, the definition of the transfer distance, the longitudinal distance. This is just the blue line is the results I was showing you. The red is a different analysis of the same data. And this is the Planck predictions. Now, right now, this is 95%. Planck prediction is a little far from that. I mean, I don't know, you can take that extension. I think that this will disappear when more data is added. But the interesting thing is that now this is the change in the scale factor. And then, so this is the derivative of the scale factor. So essentially here what you see is that as time goes by, redshift goes like this, time goes this way. So as time goes back, the universe is decelerating and decelerating and decelerating. And then a redshift of about 0.8 starts to accelerate. And the idea with DESI is actually to cover all this region. So to cover really the deceleration region with detail, and then now with the experiments that are being done now, you essentially map the accelerating region, and then this is the information that will allow people to understand in detail what dark matter is, one hopes at least. So now let me move a little bit. These were measurements of distance. Now you can also try to understand how the scale grows. And that is important because the growth of scale is what allows you to test general relativity. So essentially, if you don't know much about general relativity, if you're a student, you can actually use Newton. So because in the linear regime of gravity, they're essentially the same. So essentially, you get the equation of continuity in which you say the amount of energy density they have in a volume, if that changes with time, it has to be equal to how much it flows through the walls. Through the surface in that volume, it has to be 0. Or you can just use Newton. If instead of density you put momentum, the amount of momentum may have a volume, you compare that with the amount that goes throughout the surface, and if it's not the same, there is a force. So this is Euler's equation. And this force is what Senatori was talking about. This is essentially the derivative of the density, the derivative of the gravitational potential, and as he was saying, all the nonlinearities eventually we'll be able to include in this, just adding more terms to that, and that will be fantastic, because it's a simple picture. So if to that you add Poisson's equations, and then you just define your density contrast, which is very small, so it's just 1 plus a number that is very small. You just turn the crank with all the derivatives, you will get an equation that is just very simple. It's a second-order equation. And then if this velocity of sound is 0, like is the case after reionization, this is very simple. It's essentially, it's just an equation in time derivatives. So essentially, if you resolve this for matter, you can solve it analytically. So these fluctuations in space essentially grow multiplied by the function of time. So the shape doesn't change, it just grows. And so in the case that your matter dominated, this growth is essentially the scale factor. So that solves exactly. If it is not, if you have a gravitational constant, you have to do an integral. But again, it's a one-dimensional integral. You can do it with any computer. It's trivial. So you can actually calculate this growth. And what is interesting, so this is integral. What is interesting is that you can actually measure the growth rate. And I will show you in a second how that is done. So you can actually measure how this growth changes with time. And that can be expressed with the omega matter as a function of time now to a power. And for gravity, this power is 0.55. So if you measure gamma and you don't get 0.55, then you know that it's not general relativity. That has to be something else. So the name of the game here is trying to measure gamma. So of course, to measure gamma, you have to measure F, but it's a measurement of gamma. Now, how do you do that? And the technique is called redshift space distortions. What you do essentially is you play the same game you were playing with baryon acoustic oscillation. Remember, I was telling you there is this sphere. Well, now if you look at transverse distance in a longitudinal distance, this is the sphere that you see, right here. Now, in the case of baryon acoustic oscillations, all you do, you just use the position of this circle, if you want, for your measurement. Now, this plot has a lot more information than the peak of the circle. This plot has information of the entire structure. So from this structure, you can actually extract the value of F. And the reason is very simple. You are measuring redshift. You are not measuring position. You are measuring redshift. So if you are looking longitudinally and you have a galaxy that is moving relative to their co-moving coordinates, that will change the redshift. If that galaxy has a certain velocity with respect to you, so then that will change the redshift. So essentially, if that galaxy is moving, and if it is moving, that means that F, because it's just changing how this matter is actually changing. And then if that, you are actually measuring F2. And that's why it's called redshift space distortion. Essentially, you're measuring redshift. In redshift space, things are distorted. If you can actually predict this shape, you can measure F. And I say, actually, if you can predict this shape, and I say it purposely, because gravity works linearly until it scales about 50 megaparsecs. Once you get into this part of the plot, then you have to deal with nonlinearities in general relativity. And that is a problem that theories cannot predict very well. That's why I think Senatori's talk was so nice. If they can actually make predictions, we as experimentalists, we have the information. Except that to use it, somebody has to predict with enough precision for us to actually be able to fit. We need the shapes. So those measurements are now starting to be done. And here is an example of a data released in May of this year. Essentially, this is the same data that was used for varying acoustic oscillations. You're not surprised about that, right? Except that now they are trying not to fit the position of this peak. They are actually trying to fit the shape. And for that, you need a prediction. From that shape, you can actually extract F, and this is a measurement of F. Actually, there is a little detail, which is you're actually measuring, you're not measuring an absolute number, you need the normalization of the power spectrum. So really, you are measuring the normalization of the power spectrum that is called sigma 8 times this growth rate, which is called F. Now, you can get sigma 8 from Planck or from other measurements, and then you will measure it. But here is the product of sigma 8 times F as a function of redshift. The measurement I was just showing is this number here. This is other experiments are doing the same thing. I just picked the one with the smallest error, and also the ones that I know because I know they are colleagues of mine. And then this is the one square here. And then if you get the value of general relativity, which is 0.55, you get the value for sigma 8 from Planck, you get 0.46. So this is, so 0.46 is like this. These measurements are consistent with general relativity. But of course, the name of the game is trying to reduce these error bars and see if you can actually measure gamma within a fade with enough precision that you can actually say something about general relativity. Okay, so until now, there has been a bias. Because really, as you all know, most of the matter is in the form of dark matter. We have been measuring galaxies or the hydrogen and assuming that either the hydrogen or the galaxies actually follow the dark matter. But it will be nice to actually go and check and measure the dark matter directly. And that can be done with weak lensing. This is a technique that DES is going to really make use of it extensively. The same thing happens with LSST or with Euclid. And just because it's a new technique, a lot of people in the past had a little bit of skepticism if it was going to work or not. Now it appears that it's starting to work. But the nice thing is that actually what happens is that if you have a galaxy, and then that galaxy is lensed. Now, it's lensed not in the sense of having here a huge cluster that has so much matter that you see the arcs, the lensing in the form of arcs. You actually have the matter distributed all over the universe between that galaxy and you. The lensing is weak, and all you see is that galaxy essentially looks elliptical. So you can actually, here are some examples. So you get your galaxy, you can calculate this, the average of the intensity is just, you normalize it to a constant, and then you just calculate the quadruples of these. You can build these two numbers. Those two numbers tell you how elliptical that galaxy is. Now, of course, you say, well, the galaxies are all elliptical. If nothing else, even if they are round, they are not just all point at us. So what do? Well, you do this in a statistical way. You have two contributions. You have the intrinsic ellipticity of the galaxy, and then you have the lensing. And you do this with a lot of statistics. You just calculate the correlation between the two. And what you expect is that the intrinsic part will average to 0. And then if you have enough statistics, it will average to 0. And then eventually, you're only left with the part that has been produced by the matter that was between your galaxy and you. And you can actually do this in slices. You can say, okay, I have all my data. I'm going to slice my data in colors. So that's why all these surveys have filters. It has been shown that after you put kind of 5 or 6 slices or 10 slices, you don't gain anymore. So you just put slices in color, and then you do this, you calculate these correlations for each one of the slices. And then what you see here is that this adjusts, in this particular case, is the Canada-France-Hawaii telescope. It's a 3.6 meter telescope, it's 354 square degrees, it's 5 filters, 5 years worth of data. Now, why am I telling you this? Because DES is a bigger telescope, it's 4 meters. DES is going to do 5,000 square degrees instead of the 150 square degrees, and then it's going to run also for 5 years. So one expects big improvements from DES in here. LSST will do even more. I mean, LSST will essentially cover the entire southern skies. It's an 9-meter telescope. It will do this much, much better. Euclid too. Because Euclid will do this from space, and from space you don't have to deal with the distortions introduced by the atmosphere. But anyway, this is the status. I mean, this is the way things actually look right now. So these are just the beams in redshift, and these are just these correlations. You can actually correlate all the beams with the beam with itself, and the beam with another beams, so these slices with other slices. And then the measurements are just these points with error bars right here. And then the prediction is actually, the fit is actually the black line. I mean, these other lines are important because you have contributions that you actually don't want, in the sense that when the clusters form, the galaxies sometimes get aligned a little bit. So that's called intrinsic alignment. So essentially, that alignment can create these kind of correlations that you don't want. But this is log scale, and the intrinsic alignment are just these two. And you can see that in most of the cases, intrinsic alignment is not very important. Even though you can do this in only 2 beams, and this is the same analysis done in 2 beams. In the case of 2 beams, you lose resolution. On the other hand, your systematic errors with intrinsic alignments average better. So you extract information from this, and essentially what you get is just the results of the fit. This is how you get sigma 8 with an error of 0.015. It's not as good as Planck, but again, this is a new technique. And then you get a W0 is -1, essentially, with an error of 9%. It's not the 5.5% of that you get from supernovae, but again, these are new techniques. And then, nobody knows how the systematics will really affect when you're trying to get these results, and when you try to get to sub-percent, to below 1% level. It's not like a BAO. BAO, people know that that's just a matter of adding statistics. But, if this can be made to work, it's a really powerful technique, and it's a way to actually measure all the matter, not just the matter that you see, but all of it. Okay, I have 9 minutes left. So I'm going to use those 9 limits to say, okay, so now what? Now we know that W is -1 with 5.5% accuracy. We know that WA is completely consistent with 0, so what do we do? So I will talk a little bit about the future experiments. Now, I'm going to be completely biased. Number 1, I cannot do justice in 9 minutes to everybody. Number 2, I'm more familiar with the experiments in the US, or the experiments that actually the US is involved in. So this is just the table of experiments the US is involved in. This doesn't reflect the quality of the experiments. It only reflects my ignorance and lack of time. But essentially, DES is running. The dark energy survey is running. So that's the next series of results will come from DES, I hope, being a collaborator of DES. But then these are experiments that are being built. The dark energy instrument, which is a spectrograph. It doesn't take pictures. It takes spectra of the galaxies. Then you have Euclid, which is a satellite run by the Europeans. The LSST, which is a big telescope in Chile, that essentially will use the same techniques as described. It's not different. The techniques are the same for all these experiments. And then W first, I will not cover that because, the other experiments are funded. This one is not 100% funded, but, we have enough money right now that we are just running full speed ahead. So let me tell you a little bit of each one of them, of each one of these experiments, what they do, or what they are going to do, and then what sensitivity they are going to achieve, and then I will stop. So DES is just, I mean, I hope I gave you the idea that the name of the game is number of galaxies. You don't want to know the detail of the galaxies. What you want to know is you want to measure the position of the galaxy, you want to measure the shape of the galaxy, and you want to measure the distance of the galaxy. You don't care about any details of the galaxies. You just use the galaxy as a tracer. The same thing is when you study the hydrogen cloud. You want the shape of the hydrogen over big distances. Now, I didn't tell you, but to give you a sense, this ruler is 150 megaparsecs. Linear relativity kind of goes up to about 50 megaparsecs. A galaxy is about 100 kiloparsecs. So a galaxy is tiny, it's a little point compared to the things that we want to study. A cluster of galaxies is about 20 times bigger. So it's about 1 to 2 megaparsecs. Still small compared to 150 megaparsecs. Non-linear, so if you go another factor of 20, you get into a regime in which gravity starts behaving in a linear way. So to some extent, the pictures that you take cover a region of sky that is very big. 150 megaparsecs depending on how far you are, but typically several times the size of the moon. So essentially, when you're looking at the sky, you are interested in scales that are bigger than the moon. So you don't care about the details of the galaxy, you just want many galaxies, millions of galaxies. So you build telescopes that don't have a little field of view and can actually do extremely good, measure really good detail of that, like the Hubble Space Telescope. You really build a telescope with a big field of view and try to measure as many galaxies as you can. So that's what DES did. It's a big field of view. The moon looks like this. So, every time you point the telescope, you're covering something as many times the size of the moon. So again, it's a 4-meter telescope. The important part is just it has 5 filters, so you can put slices, 5 slices to do glancing, and then you just cover as much area of the sky as you can. So in this case, it's 5,000 square degrees. So since we are running, and since we are very proud of having built this camera, let me show you some pictures, do some propaganda. This is just one CCD. This is the way the raw data looks like. And then you make this uniform by actually pointing the telescope to something that looks white and very flat, and then you correct all your CCDs. You do this in several filters, so now you can combine them, and unfortunately, you can't see much. But if you go look at the talk, you will see the colors of galaxies, and you can by eye identify clusters and things like that. And you will see that here there is a group of galaxies that they all look red. So clearly, they are all together. So essentially, you're just trying to measure galaxies. And for each one of these, you measure the shape, you measure the position, you try to get an idea of redshift. This was something that was very nice. I mean, one of the nice things about this field as an experimentalist is that when you're doing Tevatron collider physics, you can't show pictures. You show a picture of the detector, nobody cares. So now, you show a picture of a galaxy like this, and it's kind of nice. So I'm going to make use of that. Right? Essentially, this is one of the first galaxies that DES measured. Now, DES started making measurements, and a few days later, it started just measuring this taking this fantastic picture. So this is one of the galaxies that DES measured very early on, in September of 2012. 2 months later, the Hubble Space Telescope was looking at the same galaxy, and boom, a supernova. So now, this is something that DES is doing continuously. There is a field that DES goes every 6 days and remaps that field every day. It's every time. So, every 6 days that field gets remapped, then supernova gets identified. Give a supernova, if you can determine it's a type 1A, you actually go look at a telescope that has a spectrograph, and then you run a spectra on that supernova to just determine the redshift, the intensity decay, and everything. Anyway, so from DES alone, these are the 4 pros. I was telling you galaxy clusters I didn't talk about, but it's fairly simple. Essentially, you count clusters as a function of mass. And, it's simple saying it. It's not that easy to estimate the mass of the cluster, but if you can count clusters as a function of mass, then you can predict how many clusters there are going to be, and you can check your predictions against the number of clusters. So it's clusters, weak lensing, binary acoustic oscillation, supernovae, and then all this combined is just a prediction of DES alone without combining with anybody else for the parameters of dark matter. Now, this is a spectrograph. It's the same telescope, but in the case of DES, you take pictures, you do imaging. Really, if you want to determine the redshift of a galaxy really well, what you want to do is actually take a spectrum of that galaxy. So in this particular case, there are 5,000 fibers, moved by little robots. You actually, every time you point your telescope, you point those 5,000 fibers to 5,000 galaxies. Then the light gets into the fiber, you send the light to a spectrograph, and you take a spectra. And then you do that for many galaxies. In this case, it will be about 20 million galaxies, a little over 500,000 quasars, and then you do BAO. And then, you measure this distance scale using this ruler that is called BAO. Again, this is what I was telling you. If you look at how the scale factor changes as a function of time, the derivative as a function of time, these are the error bars that are going to, this is the error bars that DESI is predicting for that measurement. So you can see that after this run, this is going to be, all this is going to be known very well. Okay, so these are just a measurement of W0 and WA, prediction from DESI, and this is just F again. But I'm going to point something out here that is related to the talk, the cosmology talk by Senatori. These are DESI predictions. This is a prediction of being able to use modes up to k of 0.1 inverse megaparsecs. And that's more or less where linear general relativity starts having problems. If you actually can go to 0.2, then you can get into this ellipse, into the dotted line. If you can predict to more than 0.2, and he was saying that they can actually predict to 1% to 0.6, then this ellipse is going to dramatically shrink. So even though the measurement will be there, the ability to actually make full use of that data will depend on the ability of theories to predict. Stop. Okay, I thought I had 4 minutes left. Okay. That's okay. That's okay. So Euclid, right? Do I have 1 more minute? 1 more minute? Okay. So this is Euclid. Same thing, same game from space. Except that now, you're in space, the coverage is bigger, you get more galaxies. Essentially, this is a prediction in WA and WP from Euclid. This is the way they will map F, right? The way the scale structure is growing. And LSST is another big telescope in the south. And then these are the results for LSST. I will not say much because I ran out of time already. So let me conclude. And my conclusion will take a few minutes, even though there are only 3 bullets. So all experimental data available today is completely consistent with the cosmological constant. Is that surprising? I don't know. I will address that in point 3. Point 2 is in the next 15 years, W will be known to a fraction of a percent. I hate to put a number here. You can take the number for Euclid, that is 0.7%. But if theories can actually improve the prediction, that number may be reduced dramatically. So it's a fraction of a percent. WA will be known to a few percent. Euclid is saying that it's going to be 4%. But again, these things can improve, but the number is about a few percent. Now, we all hope that after all this work, after spending another decade and a half doing all this work, one will find a little bit of discrepancy. Okay, what if there is no discrepancy? And then the discussion, of course, I may not care because maybe by then I will not be able to do all this business just for natural reasons. But for the young people in the audience, the discussions that people are having today are important because people will say, well, everybody will get tired. There's really no theory. There is no concrete prediction of what to test. So at some point, people will get tired. So people will not want to spend any money, will not want to spend any time if after, after 15 years of doing this, we still can't tell. Well, perhaps not. If you're young, your view may be a little different. So let me just spend a few seconds telling you why. So this is what if we don't see anything. Josh Freeman, Josh Freeman gave a little informal talk a few weeks ago at Fermilab, and he was trying to compare inflation with dark matter. He was saying, okay, inflation, the original inflation went through something like 60 folds, and we know we are here, so we know it was not a constant. At some point, inflation ended. So what if what is going on right now is similar, is that the same kind of inflation? Then the question is, okay, what would an observer, if there was an observer there when inflation really started in the first E-fold, what would happen if that guy is thinking in terms of W0 and WA? They don't know anything about potentials, they don't know anything about theories, they are just trying to measure W0 and WA. What would they see? Well, you can actually get some idea because Planck puts limits. And limits that they didn't publish yet, so this is personal communication, gives you a number of W0 that is essentially -1 to a few %. So, somebody inflation at that time will be measured W to be -1 to really high precision, a fraction of a %. And they will measure a value of WA that is very small, much smaller than this few % that we will measure after 15 years. So perhaps the idea that we have two inflations and they may have something in common is fascinating enough to actually get young people to go beyond what we will do in the next 15 years, even if the results are all completely consistent with the cohomological constant. So thank you for listening.
Thank you for your nice presentations. Questions?
Just a comment about your last sentence. Even though perhaps inflation would have an equation be very much close to the cosmological constant, the fact that the perturbations and S running of it is not scale invariant measured, then it implies that it wasn't a cosmological constant, basically not W = -1.
For inflation?
Yes.
Yeah, of course. I mean, inflation ended, right?
Well, so not only ended.
And the spectral index is not 1.
But it's not that it, yes, it ended, but it's not.
Yeah, the spectral
it didn't go
index
to
is not
-1
1.
to.
Yes, of course, absolutely. I was just trying to say, okay, what if an observer was there, not at 60 folds, but at half a fold?
But then there's in the structure formation perhaps that we can actually also see the equation of state in dark energy.
So, sorry, Axel, I couldn't hear.
Also in the way the perturbations grow, perhaps we can also measure the equation of state there.
Sorry, I should have mentioned here. I mean, if we measure gamma and gamma is not 0.55, that will be revolutionary, because that would mean that general relativity, there is another theory that beyond general relativity, absolutely. I mentioned it during the talk, but I didn't say it here. Thank you.
More questions or comments?
I guess I have the inverse question. I mean, supposing that one assumes that W is equal to -1 within an uncertainty which is much less than your experimental uncertainties. And so one just has to turn the whole thing around and use this as a test of one's conventional ideas about inflationary cosmology. So there's a whole bunch of issues there, like non-Gaussianities, like trying to overcome cosmic variance and so on.
Yes.
So this program that you outlined, how much does it do in that direction?
Well, I mean, non-Gaussianity, I don't know, that's I always feel there's a little bit more about the CMB, right? And you can also test it here. If you tell me, to comment about non-Gaussianity, I don't know much about it. So, that probably will be for the people of the CMB. I don't know about non-Gaussianity.
Can I ask you mentioned for supernovae that now they're limited by systematic errors,
yes.
and then that BAO is much better. That for a while it'll be limited by basically counting statistics,
yes.
but then there's also a lot of work on nonlinear corrections.
Yes.
Could you maybe say a little about what is known about the sort of systematics and ultimate limits of what you can do with these different techniques?
In the case of supernovae, you are trying to measure the intensity. And you are trying to predict, based on your time curves, you are trying to predict the intensity, the original luminosity of the explosion of supernova. So that involves, the atmosphere, when you're trying to measure the intensity here. So, you know, the atmosphere counts, your filters count, the relative normalization of the filters between different experiments count, all that counts. When you're trying to do VAO, you only care about the position of the galaxy. So, you know, you measure the position of the galaxy, which in angles can be measured extremely well. And then with a spectrograph, you measure the redshift. And the redshift is measured like 2 orders of magnitude better than you actually need to measure 150 megaparsecs. So really, the systematics are not there because you measure the position of the galaxy extremely well, both in 3 dimensions. And all you care is about those 3 numbers. You care about that redshift and the 2 angles of the position of the galaxy. So that's why it's not like a supernovae that you actually have to infer what the original luminosity was. In this case, you measure all you need to measure extremely well. So that's why the systematics are not important. Now, with respect to the prediction, you know, getting into the nonlinear regime of general relativity, you are trying to measure the position of a peak. It is true that you have to kind of fit the peak, but even if your prediction is not extremely good, if you say, okay, at 150 megaparsecs, even if gravity is not perfectly linear, the corrections are small. And on top of that, you're trying to measure just the position of that peak. So it's a measurement that is a lot simpler. So that's why it doesn't have the systematic errors that the supernovae have. Right?
Can you say some few words about different models like quintessence or in your?
I'm not a theorist, no.
But
so
you just check in a model, but can you?
Yeah. Here there are, I can tell you what can be achieved. So for example, in here, right? I mean, this is lambda CDM. So this will be a curve that essentially has a power gamma of 0.55. So these are now 3 different models of extensions of general relativity. So with DESI alone, you know, with this kind of error bars from DESI alone, these models will be either confirmed or ruled out. Now, I mean, theorists are really smart people. They will come up with different models, I'm sure. But, you know, this gives you an idea. If you have a model, you can actually calculate this, and those are the error bars in the prediction. If you go to Euclid, actually it's even better. Because if you go to Euclid, then actually, you know, they go to higher redshift because they are in space. And actually, the error bars are even smaller. So you can actually test general relativity even better.
Okay, I don't see any other questions. So let's thank our speaker again and start. And let me invite to speak Professor Joseph Neer from Weizmann Institute. The title of his talk is Flavor and CP Violation. The title is Flavor Physics.